Hello, Physics 20s. We are going to go through some of the principles of circular motion as they apply to planets in orbit. And I really like talking about this. I want you to be prepared, though. There is a lot of complexity to doing the math here, and I want you to be patient as you start into it because it's easy to make mistakes. So I'll try and highlight some of that as we go. But I want to talk about this man. His name is Johannes Kepler. And he was a mathematician who made some really significant observations. What's even more miraculous is that he made them years before Isaac Newton. And basically, in Kepler's day, everybody thought that orbits were perfect circles, and that's an easy conclusion to make based on their observations. What he did, though, is he carefully analyzed the orbit of Mars. He got some data from an astronomer named Tycho Brahe. I think I'm saying his name right. And when he plotted it, he realized that the orbit of Mars did not quite fit a perfect circle. He couldn't make it fit. And he did understand math, though, at his time, and he understood the shape of an ellipse. And what he concluded was that Mars' orbit was actually an ellipse. And so this led to him doing some other observations, but he basically has three laws. You need to know all three of them, and I'm going to go through them with you right now. So the first one is that all orbits are actually ellipses, not circles. As you'll see, a lot of the planets have ellipses that are really, really close to a perfect circle, but they're just off by a little bit. And you need to know the basic anatomy of an ellipse. So here's just a picture of this here. An ellipse is an oval that has two foci or focuses. Okay, so you can see in here. Maybe I'll just come in. There's a focus right there, and then a focus over here, and those two focuses are where the axes run through. Okay, and I'll show you an animation of this in a second, but it should make sense. What we should note here is there's obviously a major axis, which is the horizontal axis, which is much bigger, like a much bigger diameter than the minor axis. And as you can see, at any given point as you go around the ellipse, the radius is constantly changing. Okay, for our purposes, whenever we deal with ellipses, when we deal with orbits, we are going to use half of the major axis as our radius. So that would basically be this region right in here. Okay, that is we call it the semi-major. Semi means half, like a semi-truck is two parts. Semi-major. Okay, and you should make note of that because that's what we use for the radius, okay, the semi-major axis. The other axis is, you can note it if you want, it's actually, when we cut the minor axis in half, sorry, that was a little ugly, we call that the semi-minor axis. Okay? But it's the semi-major axis that we use for our radius. Now, just to show you that, now there's another principle of ellipses, and that is they have a property of eccentricity. Eccentricity, really the root word for eccentricity is eccentric. If you know someone who's eccentric, it means they're weird or they're odd. So eccentricity is really a measure of how odd this circle is. Okay, it's measured on a scale from 0 to 1, 0 being a perfect circle and 1 being a really elongated ellipse. Okay, so here actually what I'll do is I'll pull this up here so you can see this. Here we have, on the left here of your screen, we've got an ellipse, but what I can do is I can change the eccentricity of the ellipse. So this is a really eccentric ellipse, but I want you to see, and you can see the two blue dots are the foci, but when they get right, if there's only one focus, then you have a perfect circle and you have an eccentricity or an oddness of 0 because you're not odd, you're a perfect circle, if that makes sense. So we could change this in either direction. I could make the semi-major axis go up like it does here, or I could make it go horizontal. So whatever, we're making an ellipse. But it's actually really easy to make an ellipse. You just get, you get two like tacks and stick them into, say a piece of cardboard or something, and then you loosely tie a string around both of them, and then you stretch the string until it's tight, and then you go around so that it's catching both of your tacks, and you will just be able to scribe out an ellipse. So we don't need to know the math beyond that, but you should be familiar with the semi-major axis and the semi-minor axis, okay? And it's always the major axis that we use, but that's just kind of a fun application of understanding ellipses, okay? But you do need to understand eccentricity. So let's go back to the notes. So here, the second law, this one's really interesting. The second law is, I'll read it quickly. It's an imaginary line from the Earth to the Sun will sweep out equal areas in equal time periods. What does that mean? Now, it does mean that the orbital velocity will vary, but let me show you that in another animation here. This one here, this is an awesome simulator. I really like this. So actually, we can just review Newton's first laws really quick. Kepler's first law. So see, we have basically when you have the sun and a planet, the sun is one of the foci or one of the focus points, and then there's an empty focus point, okay? So if a planet's in orbit, you can see this animation going, if the orbit is really eccentric or it has a high eccentricity, then you can see here that the velocity of the orbiting body actually speeds up as it gets a little bit closer to the sun, and it slows down as it's farther away from the sun. This is actually quite characteristic of comets. Comets that orbit the sun have classically super eccentric orbits. So anyway, here's the semi-major axis, right? Because the center would be right here. There's the semi-minor axis just for reference, but again, we for our math, we use the semi-major axis. And as you'll see, most of the orbits we deal with are really close to a perfect circle anyway. So this is an extreme. Yeah, radial lines here. So here, this is what I mean by using a piece of string. If you used a piece of string and wrapped it around those two tacks, you would get, it would basically look like these green lines as you kind of scrolled around and made the ellipse. So that's kind of cool to see in terms of the anatomy of an ellipse. And of course, yeah, if we change the eccentricity, of course, if it was a perfect circle, then obviously this is what it would be. And the semi-major and semi-minor axis would be the same because it's not an ellipse. But yeah, then this happens and we've definitely got an ellipse going on. So let's go to the second law. And actually here, let me clear off all that stuff. So if we get a really eccentric, it's kind of fun to get actually, wait, let's start with an eccentricity of 0. So in Newton's second law, or Kepler's second law, what we could do, here, let's erase these and let's do a continuous sweep and try that. Okay, so basically, and this is a fractional sweep here. Let's get that back to, let's do 1/12. That actually makes more sense here. So if we wanted, what we could do is, if this was the Earth, we could sweep out the area for 1 month. Okay, so obviously this is a simulation is much quicker than a year, but if we say, okay, we're going to sweep out 1/12 of the Earth's orbit, so that every single area that we sweep out there, we just did it, would represent the time for 1 month. So and as you can see, every single portion is equal. It's like, we have a pizza here and we cut it up into 12 pieces. All the area of each slice is the same. Now, what's really cool is, here, let's erase this and let's make it an ellipse now. So this is, and we'll make it really extreme just for fun. So, because it will emphasize the change in velocity. So let's start sweeping now. So now it looks a little bit different because when you're farther away, the slices get really thin. But as you get close to the sun, look at how kind of wide the kind of the crust of the pizza is, if you will, on the edge. But the point to make here is that if we had a pizza in this shape and I cut it in this shape and gave you all a piece, you would all get the same amount of pizza. The area is the same. And so that's what Kepler was emphasizing, equal areas in equal time periods. It's kind of cool to play with this. I guess we can kind of shift it back and forth. Okay, so there was the eccentricity of 0. We can go way up to an eccentricity. This one will take it to 0.7, not quite to 1, but that's an extreme. Okay, so I don't know if I can show it doesn't look like I can show I can show the velocity, but not with a vector. That's okay. So I think you can see it though still. You can see that this blue, or sorry, the white object, the satellite, it travels slower as it gets far away from the sun. But when it gets really close to the sun, it goes much, much faster. So the principle you need to know is, yes, equal areas in equal time periods, but what it really means is that the velocity of an orbiting body varies as it goes around its orbit. Primarily, it goes much slower when it's really far away from the planet, or the sun in this case, and it goes much faster when it's closer. I can show it. There it is. That's what I wanted you to see. So there's the velocity of the orbiting body. Watch how it increases, of course, as it gets closer to the sun. But it's a centripetal velocity, so it's tangential to the curvature of the orbit. Excellent. So that leads us then to Kepler's third law. And there really isn't much of an animation for that, but you can, just for fun here, let's show you quick while we're on it, Mars's orbit. Okay, so Mars actually has an eccentricity of 0.093. I noted that in the example in the notes, and you can see that it is almost a perfect circle. Like this animation has a hard time really showing any degree of variability, just a little bit, but it's and most of the planets that orbit our sun do have an eccentricity pretty close to 0, because just due to the nature of their orbits. So let me pull back the notes here now, because what I want you to see is Newton's third law. So this is the big one. This is where the math hits the fan, basically. What Kepler realized is that for all planets that are orbiting, say, the sun, their ratios of their orbital periods squared divided by their orbital radii cubed. This is a really interesting ratio. But he observed with all of his math that ratio would be a constant. Now, for all the planets. So if you took the orbital period of the Earth and the orbital radius of the Earth, you squared the period, cubed the radius, you'd get a number, okay, a really ridiculous number. But if you did that for Mars, you got the orbital period for Mars and the orbital radius of Mars. Both those numbers would be much bigger than the Earth, because Mars, of course, is farther away from the sun. But if you did that same ratio, you'd get the same number. And that's amazing to me. That's just, that Kepler could figure that out was just mind-blowing to me still. So it means then that every single planet that's orbiting the sun will have that same ratio. And there's a lot of power in that math, which you'll see shortly. So we could also say, like I said in the example, all the moons that are orbiting Jupiter has I know it's got 9 big ones and there's some other small ones. I can't remember the total number. But anyway, all of those moons that are orbiting Jupiter would have the same Kepler's constant. Okay, and that is measured as K. So you can see that down here. Capital K is known as Kepler's constant, and it's equal to the ratio of the orbital period squared divided by the orbital radius cubed. Now, these other formulas here won't make a lot of sense until I define them, but Kepler's constant is the very foundation for all of these. Now, what's so cool is that Kepler, I'm skipping ahead here, his observation was made years before Isaac Newton even explained what gravity was. And so that makes Kepler's discovery all the more impressive. Now, what we know though, and what you should be prepared for, is if in any question you know that an object is in orbit, if you see the word orbit, okay, in a question, what that means is that the force of gravity is the only force causing the object or the the planet or the satellite to go in a circle or in an ellipse, okay, in a circular path. Gravity is the only force. There's no strings. There's no venting volcanoes that are causing a force. Like, I don't know what else would cause it. But the force of gravity is the only force. So this is where we start right here. We say that Fc is equal to Fg. And what we're going to do here is show you how to get Kepler's constant from this. So there's one way to do it, and that is to use the centripetal force formula that you've learned before. Maybe you haven't used it too much yet. It's m times 4 pi squared r, over t squared. That's going to equal, we're going to expand the force of gravity formula into the big one, g m1 m2 over r squared. Sorry, my pen is not amazing here. Okay, so in this expression, m2 is the same as the mass of the satellite. Okay, m1 is always the big mass. That's like the source mass, sometimes we call it. So if we're talking about the Earth orbiting the sun, then m1 would be the sun, and then m2 would be the Earth. Okay, now that'll change, of course, if you're dealing with a moon around Jupiter, but you guys can adapt that pretty easy, I think. So it means, though, then that m2 is the same as this m. So those two m's cancel. Okay, and then what we do right here is we need to move the period squared so that it gets above the radius. We're trying to actually make Kepler's constant out of this mess right here. So I'm going to get t squared out of the denominator and move it over to this side, okay, over to the right-hand side. And I'm also going to divide by the radius. So then I can cancel that radius, and I can also cancel t squared from this side, okay? So that's going to move t squared over here, and it's going to bring an r down below, okay? Now, I still have 4 pi squared on the left-hand side, and I have gm1 on the right-hand side. So if I divide by gm1, okay, I'll maybe show that here, then I can get rid of that. And then let's just summarize this, because you can probably see where I'm going now. What we're left with then is 4 pi squared. Oops, sorry. Oops, not r. 4 pi squared over gm1. Big G times m1 is going to equal t squared over r cubed. Now, actually, I want to show you something with this. Let me just change that a different color, and then you'll see why in just a second. So this is Kepler's constant, t squared over r cubed. Okay, that equals Kepler's constant. And what's really slick here is Kepler's constant can also be equal to 4 pi squared over gm1, if you can see that right there. Okay, now I did these in different colors to make a point. Over here, t squared and r cubed, those deal with the satellite, if that helps you. So the satellite, the orbiting body, we need to know its orbital period, so how long it takes for the satellite to orbit, and to go around once. And r is the orbital radius, and that's always going to be from center to center. I'll show you that on your formula sheet in a minute. But r is the distance from the center of the planet to the center of the sun, or whatever it is. Okay, so but t and r deal with the satellite primarily, okay? The only property out of all of these variables that is related to, or that comes from the planet, okay, or from the sun, the orbit, the body that's being orbited, okay, the only variable is the mass. And there it is here on the left. So this is the mass of, we can say, the planet for our example here, if we have a satellite orbiting a planet. Um, so what's really interesting about Kepler's constant is if you are trying to say find Kepler's constant for a star or for a planet, the only thing you only need the mass of the planet. You don't need the radius of the planet, like the physical radius of the planet. You don't need to know how fast the planet is spinning or anything like that. All you need to know is the mass of that planet. And what's super powerful about this math is this is how we actually get the mass of a planet. If we want to know the mass of a planet, all we have to do is send or at least observe a satellite that's orbiting that planet. So if we want to know, say, the mass of the moon, all we got to do is send a satellite up to the moon and have it go around the moon. We've done that lots. We've sent astronauts to the moon, and we can time how long it takes for the spaceship to go around the moon once, and we can use lasers or use radar. We can measure a distance from the spaceship to the moon surface, and then do a calculation and get the actual orbital radius. We can do that stuff. And this is what is so impressive to me is if you just get the period of a satellite and the radius of a satellite using this equation that I'm showing you now, you can solve for the mass of the planet. And that's how we get the mass of all the planets, the sun, everything. It's awesome. I mean, how the heck are we going to get the mass of a planet? You can't put a scale underneath it and try and measure it. My goodness, these things are monsters. So it's the math that gives us that power, and it's just really impressive. Anyway, so now this isn't the only derivation that we can use, and I'll show you the second one here. And I know I kind of started writing into it because we have another option for the centripetal force, and that is this guy. We can use mv squared over r and make that equal to big G m1 m2 over r squared. Again, the m2 and this mass, if we're measuring the the centripetal force on a satellite, that mass and this mass both cancel. And I think on your formula sheet, I think I just left it like this. I just left it as v squared. I didn't take it further than that. I said that v squared is equal to gm1 divided by r. Okay? Because what I'd do is I'd multiply both sides by r. You can maybe see that now. And I can just get this v. And this velocity actually is, it's known in rocket science as an escape velocity. I'll talk more about that a bit later on another video. But if you're doing a calculation and you need to know how fast you need to get like a spaceship or a space probe, how fast you need to get it going so that it will actually leave the gravitational attraction of, say, Earth. So if we want to send a space probe to Jupiter and we need it to go fast enough to get away from Earth's gravitational pull, this is the formula that you can use to determine what that escape velocity is. So you determine that, and then you make sure you just go faster than that, and you're gone. Okay, you're on your way to Jupiter or wherever you're going. Okay, now there's two possible I guess summaries for using Kepler's law, and you'll get a little practice with both of them as we keep going here. So there's one more formula there that I need to just describe here quick. And this is where you'll use another variation of Kepler's constant. So if we have two planets or two satellites orbiting a planet, okay, so let's take the Earth just as an example. And maybe we have the International Space Station. It's orbiting at like 400 kilometers above the Earth. So, there it is there. And then we have another satellite that's way the heck out here. Okay, we'll talk about a geostationary satellite, actually. That's kind of a fun um, application of these principles. But there's another satellite way out here. So we have two orbiting satellites. Now, as we know from Kepler's constant, both the International Space Station and this satellite will have the same Kepler's constant. They are both orbiting Earth. So if we do their t squared over r cubed for both of them, it'll be the same number. Now, that has a lot of power, though, because if you know at least three of the four variables, you can find the fourth one really easily. Okay, because really what we're saying here is that t squared over r cubed for the we could call the International Space Station A, and we could call the other satellite B. And so what we can say then is this middle expression right here is that t squared over r cubed for the International Space Station will be the same as t squared over r cubed for this, if we're going to use the geostationary satellite, so be it. Okay, so but they will equal each other. Now, and so the power is, if I gave you three of these variables, let's say you knew these three variables right there, but you didn't know the orbital radius for the geostationary satellite or object B, whatever it is. Then you can just cross multiply and divide. Okay, now the numbers are kind of ugly, but just be patient with them, because you're cubing and squaring and all that stuff. Sometimes you'll swear. No, you won't. You'll just cube and square. That's what you're going to do. But then you can solve for whatever variable you need. Now, so I simplified it just a little bit on your formula sheet, and all I did is put all the periods on the same side, okay, and all the radii on the same side. So what you have on your formula sheet is this expression right here. Ta squared over tb squared is equal to ra cubed over rb cubed. Okay, so that's a quick introduction to the formulas, and there is definitely some complexity here. In fact, what I should also just emphasize is, I think I have it pulled up here, not that one. Yes, this here. So you're going to use this a lot as you get going into some of these practice questions, and I'll probably make a few videos of a few of these questions just so you can see how they're done. But you can see here the columns here. This one here is the average radius right here, okay, in meters. That's the physical radius of the planet, okay, if you happen to need that. But the masses of all of those, all the planets, including the sun, are listed. And then the distance. This distance is an orbital radius. That means it goes from the center of one planet to the center of the other, or to the center to the sun, okay? Because this is the distance from the sun. So you don't need to be adding the radius of the individual planets to this number or anything like that. These numbers are huge already. And it's worth noting, because it'll come up later, we are going to use astronomical units, AU. You can see that there listed. An astronomical unit is the mean distance from the Earth to the sun. It's just a nice little ratio. And we use that actually because it makes your math easier. You'll see why. Instead of using 1.49 times 10 to the 11th, you got to mess with that number. You can just use 1. And 1 cubed and 1 squared is just 1. So the math gets really slick in using astronomical units. Okay, so I think that's enough for now, and but I'll look to post other stuff. And again, as you start these practice questions, please be patient with yourself. So much of this is entry. You've got to be really careful entering, big G, that's 6.67 times 10 to the negative 11. All these numbers have exponents. Sometimes you're squaring, sometimes you're cubing. You're going to have to get familiar with your calculator. You got to use the math, I think it's math 3. Like you have to push math, and then I think it's function 3 or 4, where it will cube or cube root if you're working backwards. Okay, so you have to derive, switch the formulas around and solve for the radius. Eventually you have to cube root a big mess of calculations. So again, just be patient, take your time. I'd rather you go slow than fast on this one. And I'll try and give you lots of time to get your practice in. All right.